A few more examples of being able to utilize the definition of combinations this time to algebraically prove some statements about combinations. A first example is that for all n in the integers, for all n greater than or equal to 3, n minus 1 combination n minus 3 is equal to n quantity n minus 1 divided by 2. So, a very simplistic example. You may recall that the formula for n combination r, for combinations n factorial divided by r factorial times n minus r factorial. The only difference between combination and permutation is that we now have a new factor in the denominator, that r factorial. We're going to start by defining n to be n minus 1 in the equation to the right, and we're going to define n minus 3 to be r in the equation on the right. And we're just going to do some substitution. So this is now going to become n minus 1, n minus 3 is going to be equal to n minus 1 factorial divided by r factorial, or in this case n minus 3 factorial, divided by the quantity of n minus 1 minus n minus 3 quantity factorial. All right. Now we're going to simplify a bunch of stuff here because there's a lot to be simplified. So n minus 1 factorial we can think as n minus 1 times n minus 2 times n minus 3 all the way down to 3 times 2 times 1. N minus 3 factorial, n minus 3 times n minus 4 all the way down to 3 times 2 times 1. Inside of the quantity, the n's are opposite, so they cancel each other out. And then we have negative 1 minus a minus 3, which just turns into 2 factorial. Now we can simplify, because notice in the numerator we have n minus 3, and then the next term would be n minus 4, and everything thereafter is the 3, 2, 1. So essentially what we have is we're just going to have this n minus 1 times n minus 2 divided by 2. And unfortunately, that is not the same, okay, as n minus 1 divided by 2. So unfortunately in this example we found one that does not work. So for this example we can say that we disproved the statement. So be careful, not all of these are going to be true. A second example. This time we have 3 terms in there. Okay, so it's just a little bit more algebraically rigorous. Now n is greater than or equal to r, greater than or equal to 3, and we're stating that combination n minus r minus 1 with n minus r minus 3 is equal to this right-hand side given. All right, so let's think of n minus r minus 1 as n in our formula. Let's think of n minus r minus 3 as r in our combination formula. So n minus r minus 1, n minus r minus 3 combination is going to be equal to n minus r minus 1 fact on top divided by n minus r minus 3 fact, and then we're going to take the difference of the two. So it's going to be n minus r minus 1 minus n minus r minus 3 and a factorial for that. Now we're going to simplify. All right, so n minus r minus 1 is n minus r minus 1. N minus r minus 1 factorial is n minus r minus 1 times n minus r minus 2 times n minus r minus 3 all the way down to 3, 2, 1. N minus r minus 3 factorial, n minus r minus 3, n minus r minus 4, all the way down to 3 times 2 times 1. And then finally, inside the parentheses of the factorial, we have n minus n, those are opposites, negative r minus a minus r, which are opposites, and we have negative 1 minus a minus 3. That's just going to turn into 2 factorial. Similar to the previous problem, notice that everything's going to cancel out from the numerator except for the first 2 factors. So n minus r minus 3 all the way down to 3, 2, 1, that's all going to go away. So now we're left with n minus r minus 1 times n minus r minus 2, all divided by 2 factorial. And unfortunately at this point, to be able to verify this, we're going to have to FOIL this out. So by foiling, we're going to take n and we're going to multiply it by all 3 terms. We're going to take negative r, multiply it by all 3 terms, and then we're going to take negative 1 and multiply by all 3 terms. So we're going to end up with 9 terms in the numerator before simplification. N times n squared, minus nr, minus 2n, so those are the first 3 terms, minus nr, minus r squared, plus 2r, and then our last terms, minus n plus r plus 2. And in the denominator, we can evaluate 2 factorial readily. 2 factorial is 2 times 1, which is just going to be 2. Now there are some like terms, so we're going to combine those. Notice that we have a negative nr and a negative nr, so that's going to be negative 2 nr's. We have a negative 2n and a negative n, and then we also have 2r and a positive r. So by simplification, by combining our like terms, this winds up being n squared minus 2nr minus 3n plus 3r minus r squared plus 2, all divided by 2. And if we go back up to see what it is that we're actually trying to prove, all we're trying to do is we're trying to show we have an n squared, a minus 2nr, a minus 3n, a plus 3r, a plus r squared, and then a 1. Alright, so may have made a sign error here. So negative r times negative r should be a positive r. So excuse me. So if we go back, this should be a plus r squared. This should be a plus r squared. So I apologize. We're looking to see if we get this. Alright, so that's what we're hoping to get. And notice that we have all of the terms. So we have an n squared, we have a minus 2nr, we have a negative 3n, a positive 3r, and then a plus r squared. This 2 and this 2 are going to become a 1 when we break it off. So finally, we can say that we have n squared minus 2nr minus 3n plus 3r plus r squared plus 1, since 2 over 2 becomes 1 divided by 2. And that's exactly what we were looking for. So in the final example, we're going to take a look at a more difficult type of combination proof where we're going to have to get a common denominator, much like we did before for that one permutation problem.